Right now, somewhere out in the universe, there are objects so heavy, so impossibly dense, that they punch actual holes in reality. You can't see one. You can't shine a flashlight on it because the light never comes back. And if you ever drifted too close to one, the universe would kill you in a way so strange that physicists had to invent a brand new word just to describe it. That word is spaghettification, and yes, it's exactly as stupid as it sounds. So today we're going to do the single dumbest thing a human being could possibly do. We're going to climb into a spaceship, point it at a black hole, and fall in, one step at a time, to find out exactly how and exactly when you would die. Don't worry, it's only fatal in a couple of places. First, where do these things come from? Forget the spooky cosmic monster image for a second. A black hole usually starts its life as something completely ordinary, a giant star. A star is basically a constant tug of war. Gravity is always trying to crush it inward into a tiny ball, and the nuclear fire burning in its core is always pushing back outward, holding it up. For millions of years, it's a perfect tie, but fire needs fuel, and eventually the star runs out. The moment the fire stops pushing back, gravity wins. Instantly, the star collapses in on itself so fast and so hard that it crushes an object bigger than the sun down into a point smaller than a city. Here's the comparison that makes it click. Imagine taking the entire Earth, every ocean, every mountain, all 8 billion people, and squeezing it down until it's the size of a marble. That marble would weigh the same as the whole planet, so the gravity right at its surface would be monstrous. That's a black hole. It's not really a hole. It's a place where a huge amount of stuff is packed into almost no space at all, and gravity goes completely off the rails. And gravity that strong has one terrifying rule: get close enough and nothing can escape. Not a rocket, not a scream, not even light itself, which as far as we know is the fastest thing there is. If light can't win the race out, you definitely can't. So you're in your ship, falling toward it. For a long time, nothing dramatic happens. Black holes don't suck. That's the myth. It's not a cosmic vacuum cleaner reaching out to grab you. It's just gravity, the same gravity that holds your coffee in your mug. If you swapped our sun for a black hole of the exact same weight, the Earth wouldn't get pulled in at all. We just keep orbiting in the dark, very cold and very confused. So falling in is a choice. You have to aim for it. And as you fall closer, you approach the most important line in the entire universe. It's called the event horizon, and the best way to understand it is a river heading toward a waterfall. Picture yourself paddling a canoe upstream, away from the falls. Far away, the current is gentle, easy. You can paddle against it all day. But the closer you drift to the edge, the faster the water rushes. At some point, you reach a line where the current is moving exactly as fast as you can possibly paddle. Cross that line, and it doesn't matter how hard you row or how good your boat is. The river is now faster than you. You're going over. The event horizon is that line, except instead of water, the thing rushing past you is space itself. Cross it, and to escape, you'd need to travel faster than light, and you can't. So that's it. Game over. But here's the part that messes with people. If the black hole is big enough, you wouldn't feel a thing as you crossed it. No barrier, no bump, no flash. You'd sail across the most fatal line in physics without even noticing. Now let's bring a friend. They stay safely back in another ship, holding a telescope, watching you fall. You both have synced clocks. And here's where the universe stops making sense. Near a black hole, gravity is so strong it actually slows down time. Not metaphorically, literally. The closer you get, the slower your clock ticks compared to your friends. You've actually felt a baby version of this. The GPS satellites that get you to a restaurant are higher up, in weaker gravity, so their clocks run slightly faster than ours. Engineers have to correct for it every single day, or your phone would put your house in the wrong place. Near a black hole, that tiny effect becomes enormous, so watch what your friend sees. As you approach the horizon, you appear to slow down and down. You never actually seem to cross it. You freeze, hanging at the edge like a paused video, while your light stretches out, dims to deep red, and finally fades to black. To your friend, you hang there, frozen, forever. You never fall in. But from your seat, none of that happens. Your clock feels totally normal. You don't slow down, you don't freeze. You blow straight through the horizon at full speed and keep going, falling toward the center with no way back and no way to. Even warn your frozen-looking friend that you've already crossed the line they think you'll never reach. Two completely different stories, both 100% true at the same time. That's not a plot hole. That's just Tuesday for the universe. Okay, you're inside now. There's no escape, but you're still alive, still falling. So what finally finishes the job? This is where the dumb word earns its keep. Gravity gets stronger the closer you are to something. We know this, but here's the trick. Your feet are closer to the center than your head is. Normally, that gap is nothing. Standing in your kitchen, your feet are technically pulled toward Earth a hair harder than your head, and you've literally never noticed, because Earth's gravity is gentle and you're tiny compared to the planet. But near a black hole, the pull is so violent that the difference between your feet and your head becomes huge. Your feet get yanked down way harder than your head, so the black hole grabs your feet and pulls, and your head doesn't fall nearly as fast. The result? You get stretched, like a piece of warm taffy, or a single strand of pizza dough pulled between two hands. First you stretch head to toe, then you get squeezed inward from the sides, like toothpaste forced up a narrowing tube. Longer and thinner and longer and thinner until you're not a person anymore. You're a thin stream of atoms, raining down toward the center, one particle at a time. The good news, for a really big black hole, you stay comfortably whole until you're well inside, so you get the full sightseeing tour first. For a small one, you'd get spaghettified before you even reach the horizon, pulled apart outside the door, never even making it in. Different black holes, different deaths. The buffet has options. And by the way, this exact same force is why we have ocean tides. The moon pulls on the side of Earth nearest it slightly harder than the far side, and that gentle stretch is what makes the sea rise and fall. Spaghettification is just ocean tides, turned up until they kill you. So what's waiting at the very center? Honestly, we don't fully know. Our best theory of gravity says everything piles up at a single point of infinite density called a singularity, a place where the math itself stops working and just spits out infinity, which is physics' polite way of saying, I have no idea. But let's kill one myth on the way down because you've probably heard it. People love to say that as you fall in, you'd look back out and watch the entire future of the universe play out in fast forward, stars dying, galaxies fading, the end of everything, all in your final seconds. It's a beautiful idea. It's also wrong. If you're actually falling, not heroically hovering with infinite rocket power, you cross the horizon and reach the center pretty quickly by your own clock. You don't get to watch eternity. You barely get to finish a thought. Now, for anyone who already knew most of that, here's your reward. Because black holes have one more trick, and it's the strangest of all. They're not actually permanent. Out at the event horizon, the rules of the very small, quantum physics, start leaking energy away, particle by particle. It's called Hawking radiation, and it means a black hole very, very slowly evaporates, shrinking over time until, eventually, it pops out of existence entirely. How slowly? A black hole the mass of the sun would take vastly longer than the current age of the universe to disappear. So you have time, just a lot of it. But this creates a genuine crisis that physicists are still arguing about today. Quantum physics has one sacred rule: information can never be truly destroyed. What goes in must, in some scrambled form, come back out. So what happens to you? If you fall in and the black hole later evaporates into plain, featureless radiation, where did you go? Every memory, every atom, the exact arrangement that made you you, is it gone forever, breaking the one rule that's never supposed to break? This is the information paradox, and it's one of the biggest unsolved problems in all of physics. The leading hint at an answer is gorgeous and deeply weird, that everything that ever fell in might be stored as a kind of flat code smeared across the surface of the black hole, like a three-dimensional scene encoded on a flat two-dimensional hologram, meaning the you that fell in might not be lost at all. You might just be written on the door you fell through. So there it is. Fall into a black hole, and depending on its size, you'll either get torn into spaghetti before you reach the edge, or sail calmly across the most fatal line in the universe and then get torn into spaghetti. You'll freeze forever from your friend's view and die in seconds from your own. And the deepest mystery isn't even how you'd die, it's whether the universe keeps a copy of you afterward. Not bad for...
Or a thing we can't even see. If your brain is now slightly stretched out of shape, good. That's the point. Stick around, because next time we're answering an even simpler question with an even crazier answer. Thanks for following.